doubling a line, then asking the question of doubling a square, we're presented with a kind of paradoxical solution. And so when we take that paradox of going from one level of extension to a higher extension, we say, well, there would be something similar in the extension of a cube and the doubling of a cube.
Excuse me,
And it's very useful, and this happens when you're asking young people to do this in the field at college campuses. But the first thing, an acute young person will say, what about the diagonal of a cube? And there you get the answer of a square root of 3. So it's not the square root of 2, but it's the square root of 3. It has nothing to do with cube roots. And so we're stuck with a kind of funny problem, a funny characteristic. Well, how do we even get to cube roots? How do we even generate those? And this is where we consider the logarithmic spiral. Where we clearly have a sense of a kind of power process, a quality of powers that are generated in a process of growth. And you can measure the growth, or measure your relationship to the growth in some kind of quantitative way, where it's not spatial extensions, but it does have a correlation. And the ability to quantify what is a continuous growth dynamic, which is, why Lin put so much emphasis on that notion of conical action in his development of a mathematical economics. Because going back to a constructive geometry, pre-Euclidean or ante-Euclidean constructive geometry, this remains a consistent concept going back all the way then forward to modern complex functions by Gauss and Riemann. And of course, you get into a quality where powers are available. So that language, that ability to think of such extensions, well, also as a characteristic of continuous action, provides Architis and this Pythagorean network an ability to think in a different way. And we get then the development of, we take that quality of thinking into the correlations of what we actually are required to do when we start to look at the same characteristic of just taking a process of doubling for a cube. So as we double the cube, we find that there's a different characteristic to cubic numbers, and we discussed this. You have, you can have, you have triangle numbers 1, 3, 6, and so on. You have square numbers 1, 4, 9. And then you also have a characteristic of cube numbers. And again, this is kind of this Pythagorean questions of numbers are not simply an arithmetic counting conception. There's a physical geometry. And this is what really leads Gauss to do work on the both his disquisitions on the nature of intrinsic characteristics, but it also leads to looking at the complex domain and a question of extension for to resolve the so-called imaginary or square root of -1. So this kind of Pythagorean outlook is what's revived. It's what's revived in the Renaissance, a characteristic of thinking, which then turns into what we would think of as modern mathematics. Now, you see in this characteristic that this sets up and defines our problem, that we have what we would call a geometric sequence, a sequence of, in some sense, of powers. And as we said, if you can define the outer two numbers in a geometric sequence, then the other two internal numbers are naturally unfolding, because you're defining a continuous kind of characteristic. You're identifying some underlying principle that then determines this sequence. And the same is true if we take the edges of these cubes, or these sets of cubes. If we take, well, let's redefine it. Let's now say that each of these are cubes. A cube of 1, a cube of 2, a cube of 4, and a cube of 8. If we take the edges of each of these, we have an edge of 1. Here, like up here, we would have an edge of 2. Now, it's maybe redundant, but it's, why would I move to edges? Well, just like with a square, you can define a square, since there's an intrinsic geometry, equal sides and equal angles on right angles. Once you have the edge of a square, you can construct a square in principle. What you're looking for is that length of line. So if we're looking for a cube of 2, which is intrinsically the problem that is presented to the Greeks, they're facing internal collapse. They're facing their own conjunctural crisis, much like we're facing a conjunctural crisis today. Diane kind of mentioned this last night, but the pandemic is creating the economic breakdown, but it's also the economic breakdown which is causing the pandemic. It's a self-reflexive function. And of course, it has multiple aspects beyond just that question. That just is a way of defining what becomes conjunctural. It kind of feeds on itself, I guess you might say. So if this is 1, and we define this as 2 as edges, and we're looking to solve for a cube of 2, then the natural numbers that allow this to proceed would be the cube root of 2, and then the cube root of 2 times the cube root of 2, which would be the cube root of 4, and the cube root of 4 times the cube root of 2 would give us the cube root of 8, or 2. And so we've kind of laid out then that if we can set up some sequence of geometric relationships that create 1 as an external boundary and 2 with 2 other steps, 2 other cycles within that process, then the other 2 numbers would naturally become to the cube root of 2. Okay, so that's the initial introduction of the problem and kind of a Greek approach, Archytas' approach to maybe thinking about it. Are there any questions on this that people would want clarified before we go on to the next stage?
Yeah, I guess, I don't know. I don't even know how to say this, but how, is there any other example of, say, the first element 1 and then the fourth element 2 that would give a proportional growth function? I guess what you did with the spiral doubling the square is analogous to this.
Sure.
But,
yeah, let's just take that example. Let's take 1, and then let's take the square root of 8. So I take 1, and I take the square root of 8, I've got two cycles prior to finishing off this sequence at the square root of 8. Does that make sense? So does that make sense as a way of defining a similar problem? Instead of doing 1 and 2, I could take 1 and I could take the square root of 8. I could ultimately take any number. This is just, you referenced it, and it's a useful coincidence of an example. What would this number be?
Square root of 2.
Does that make sense to you, Mike?
Yeah. Yeah.
It does? Yeah. And then this would become 2. So we set up a kind of, there's an intrinsic characteristic to this spiral. There's a 45-degree angle, and there's an increase of proportion from 1 to the square root of 2. Those two magnitudes define the physical appearance of this spiral. That, and there's one other characteristic, but it's not that important. It's the intersection of this angle. So once we set up that characteristic of growth, that's what generates the appearance of it. But this says, regardless of the appearance, regardless of how much angle you're moving, regardless of what angle it might intersect the spiral at, the basic idea is that through one cycle of rotation, in this case 45 degrees, if you get to the square root of 2, or if you say after 3 cycles you get to the square root of 8, regardless of the appearance of the spiral, the intrinsic principle of that quality of growth is still there. It's underlined in this example. And so these numbers unfold. So hopefully that at least helps to answer what you're thinking. Do you want to say anything more?
No.
Okay. Does anybody else have anything? Any other thoughts or questions? Okay, then let's get at the next.
Yeah. It seems that, I don't know, it's not really the right word, but it seems like it's kind of a question of curvature, because say you did change the angle, say you weren't doing anything relating to the square root of 2 like that spiral is, but you change the angle to 20 degrees. The proportionality, seems like to me the proportionality would be the same in the sequence of 4. And what Mike is talking about was at least something like curvature, the curvature, if you want to call it that, of the growth of the spiral is what's determining it. And as long as your 4 points are in a proportional relationship to each other along that identically curved surface, then then the proportion holds. If it did some kind of weird zigzag in the middle of it, then yeah, it would be it'd throw your proportion off, but then you'd have a different curvature. The curvature wouldn't be the same. Something like that.
Yeah. I mean, there's clearly a kind of an association of geometric growth.
Do you hear me?
Yeah.
So I was just thinking, just to simplify it as much as possible, you could make 2 different types of arithmetic growth. So you could say 1, 1.1, 1.2, 1.3, or 1, 2, 3, 4. That would also be a type of growth that would be consistent with itself. And maybe that just gives a very simple introduction to relations.
Yeah, sure. Yeah, there's different kinds of growth. I mean, in my mind, the question of the logarithmic spiral, which became kind of a funny question for this course, and it was maybe more important for a different audience, but it was to situate that there's a kind of moral association to hypothesis. That the means by which Archytas unfolds this hypothesis, and question of how did he do it, why did he do it, but that in reflecting that in some type of geometric expression, this idea of a growth characteristic to the universe itself was as an intrinsic factor. And there's 200 years prior to this period of time where you have Solon's intervention, and then you have the Ionians, the Thales and Heraclitus, and a number of rich developments from that period in around 500 BC. And what's expressive of that is a characteristic of a concept, an intrinsic characteristic to the universe as a growth factor. And I think it's just that which is the premise, though you can find other ties to it. You could express it in different ways, but that's really the main question in my mind. Hypotheses and discoveries come from a certain kind of moral passion that's identified in the universe as much as it is identified perhaps in our own identity.
I think that's what I was, trying to get at in terms of building a growth proportion.
Right.
that rather than a line, double the line, a linear extension, but an
Yeah.
actual growth function, right?
Right.
Which is really alien to the thinking of most people in our culture right now.
Right. Yeah, and why it lingers, how did Archytas come up with this? And what was the way Archytas was thinking that he developed such a hypothesis, which is really the substance of it, because the proof, you have to get familiar with the proof, just like you have to become familiar with the notes of a Beethoven, from the Missa Solemnis or the Mozart Requiem. But there's a question of then, where did this come from? By what means did he unfold this composition? How was Mozart or Beethoven thinking? And at that point, that's the domain that Lin's considering with Beethoven as a physical scientist, or think like Beethoven, and these kind of underlying questions. And so, in some sense, the logarithm at least provides a certain relationship. Okay, anything else on this section, or should we move on? Okay. Okay, so as this unfolds, we have a certain kind of language, and there's a characteristic of, we at least define the problem in a certain way that Archytas would have been familiar with just as a Pythagorean in his education. But then there's a way of how do we now define this problem in a way that's sets it up, and this may be the most really, you might say this is the most brilliant insight, maybe the aha moment for Archytas, is to recognize that he can take these proportions, these four proportions, as similar triangles, and he can replicate them within a bounded circle. So instead of having a series of four, a cyclical activity, which is characteristic of, say, a logarithmic spiral, which is an unbounded system. It's unbounded in both directions. That we can actually bind that. And, you know, it's, if you take it from a Kuzanic perspective, you could say, well, the spiral with the least amount of rotation, well, let me put it, the spiral with the greatest amount of rotation but the least amount of extension would be a circle. And then you can invert it. The spiral with the least amount of rotation with the greatest amount of extension would be a straight line. So the extremes of a spiral are either a bounded circle or an unbounded straight line. So, you know, these concepts that Kusa revives as a way of thinking are part of a language. They're part of naturally part of a pre-Euclidean language. Geometry was never for these guys formal proofs. It was never a question of assumption of physical space. It was an exploration of the physical universe. So he's got these four proportionalities that he knows he's able to conceive of. And to say, how did he come up with this? I think it's probably out of the general explorations of the circle itself. And that's why it's, in doing this kind of work, the best thing to do if you're really going to take students, young people, through something, you'd want to explore each stage. It's kind of an exploration of the circle. So like we said, why is this a 90-degree angle? Why is that A, alpha, gamma, beta? Why is that a 90-degree angle? Why does a triangle have the sum total of two right angles? Those things are not simply Euclidean proofs. They are kind of physical investigations. And can you come to know it for certain what the answer is? Yes or no, or to what sum are all triangles? So that being said, we've got this kind of characteristic, which we would call, in this case, our unit circle. And there's a question that we're asking, is that we can assume that if the circle's radius is 1, that AB would then be 2. So then we have the question, if we can make AE equal to 1, hypothesis, if we can make it 1, then we would unfold all of these proportions to be exactly what we wanted. Then so that's kind of nice. So we have then the unique challenge. And that's what we did with the method of exhaustion, where people picked different points C. And you're picking different points C, what are you looking for? Where you're saying, what point C, what point gamma, that when I come down and create a 90-degree angle along the diameter to make point D, and then up at 90 degrees to that line alpha gamma, where I get point E, what point C that I choose will put point E right along this dotted circle, a circle that has a radius of 1 around point A. And so what you end up doing is finding that there is some point C. You can either do it, you can mentally run the experiment, and see that there's theoretically some point C which would resolve the problem for us. And so then what we're left with is these unique intrinsic relationships. That the only way these proportions hold is because of the intrinsic relationships of these similar triangles. So you have to, first we're dealing with the intrinsic properties of these similar triangles that are embedded in such a way as to express kind of a logarithmic spiral. There's a self-similarity to that growth of these triangles. And there's requirements of that in terms of the angles, what's binding that sequence. And then if we have that sequence maintained, there's the question of, can we now set AE equal to 1? Can we somehow now, and it's almost always, like I said before with the cube, when you ask a young person, I don't know how many people have experience with this, when you ask a young person to say, how do you double a cube? And they say, well, draw the diagonal. When you go through this with somebody for the first time, this unit circle, because I think many people have gone through this, some of these, especially these preliminary aspects are a bit more familiar. When you take brand new people through it, they go, well, why don't you just let AE equal 1? Just let AE equal 1. It happens every time you work someone through the questions. Because there's a natural desire, well, if that's what you've got to do, it's kind of like, well, just draw the diagonal. And so there's a kind of intrinsic characteristics that how we're going to want to now solve this problem is to somehow maintain these intrinsic relationships that give us our proportions. Maintain the self-similarity of these triangles. This kind of growth characteristic of the triangles, and at the same time find a way to allow AE to equal 1. If we can do both of those things, if we can figure out some way to do both of those things, then we will have a solution to the problem without having to define any other characteristics. So that's really the kind of the second stage of this. Are there any questions on this stage? How people are thinking about it? Or anything else? Okay. So then what we're left with is what point C? What point C allows us to solve the problem? That's what we're ultimately left with. But it's a question of, we'll find the point C if we can maintain all of these relationships and let AE equal 1. So then we've got to consider how we unfold it. So let's jump into that. So we actually started with what you would intrinsically think about, which is if you really wanted to start and say, how do we increase the degrees of freedom? And we're dealing with the cube, so the idea that we can define something in terms of powers. We can define something in terms of logarithmic growth within a bounded circle, and that there's theoretically a solution in that domain is provocative. The question then, the natural characteristic would be, how do I increase the degree of freedom of what I'm confronting? And this seems like the more, like I said, this seems more like the more creative aspects of where he gets these surfaces from. And because we've been presented with the surfaces so frequently, we almost think that somehow he had these surfaces predefined, versus thinking of them as an unfolding hypothesis from what he knew he had to maintain. So who knows if he actually played with the sphere much, but what we resolved was that there was a kind of symmetry to the sphere that really he was just reproducing the same circle over and over and over again. We weren't really adding anything. And this gets at, like we mentioned, this Pierre Curie, which becomes a Vernadsky consideration on the nations of symmetry and dissymmetry. That with the torus, we actually got into a unique dissymmetry. It wasn't exactly the same everywhere. And it was this which gave us then that every point along this torus becomes C's. Well, that's provocative. So now I've got this kind of unique surface, very exotic when you really think of it. I've always thought the torus was kind of an exotic little surface. And yet now I've got all these C's on top of this surface because we've rotated the circle around point A, or some line, some vertical line running through point A. We've rotated that circle along the line of my shoulder, as if this is point A, instead of just rotating the circle itself around the diameter. Or in that case, both A and B are fixed points. So in this case, B is moving. When we talk about this line of B's, moving along the equator of the circle. Now, there may have been other hypotheses that Archytas had. We could play with it if we had infinite time. We would play with these things more. Certainly, if you were educating children, you could take a whole semester to work through this problem. That's the nature of discoveries, right? You could just take each little element. But if we consider that if these are C's and each of these points along the green line are some possible B, meaning that you've got our unit circle, replicated throughout every possible circle of our torus. And because we're not interested in any symmetries, you can just really deal with a quarter of the torus. We don't need to move beyond the very back point. That gives us a terrain that we might be dealing with. Because anytime, once you go past the back point, you're just now in kind of redundant territory, just like sine and cosine along a circle. So then we have these questions. If this is A and these are all possible B's, these are all the possible diameters, those lines. And those lines are all along one plane. They're all along one flat plane that we would think of as where the cream cheese goes on the bagel. It's a slice cut right down the middle of our torus, horizontally speaking. You could say along the equator of our torus. And that these are all where the lines AB fall. Well, in this case, if we go back to our unit circle, if you look at that line AB, A and B are on the far extension of that line. Along that line are all the possible deltas or D's. So now we say that the C's are on top and all of the deltas are somewhere along that flat plane, directly beneath the C's. Because we've got to create that 90-degree angle. So this is somehow, if we start to play with our hypothesis, if we consider the torus to be a subjunctive, let's see what happens. Then the C's become the top of our torus. The B's are along our equator. A is a fixed point. A is kind of our point of perspective. And all of the possible deltas become along this, along that plane. So now Archytas has to kind of consider something. And this is where Stuart had a certain question, because as we know in terms of our exploration, we decided to put the possible deltas along a circle. Now, these are kind of separate. You have to kind of look at these as separate, I think, because it's not like there's logical steps. There's probably a compositional interplay in terms of Archytas's hypothesis at this point to resolve Stuart's question. Stuart's question is, why a circle? Why not an ellipse? Why not some other characteristic curve? And that's answered by looking at the compositional necessity. You can say out of simplicity, you would start with the circle because you always want to start with symmetry because it'll be easier to work with. But at the same time, we know we gain advantages by adding dissymmetries, like we did with the torus. So the question is, if we're going to deal with the deltas, we have to go back to the question of how we're going to solve this problem, how we've thought of it as where the tension exists. And that would be the fact that our that what we're most interested in is this AE question. What we've really got to solve is this AE question to be 1. And the crux of it, and this is something that Bob brought up at the last class, was AE has to equal 1, and AED, the angle, has to equal 90 degrees. You've got to maintain that intrinsic relationship. Because you could always, if it didn't have to be 90, you could shift the angle over. You could shift the line to where AE is equal to 1. Well, that's really bad. Do people know what I mean, or should I draw it?
Well, isn't that also why it has to be a circle? Because ACB also has to be 90 degrees. So you have 2 Pythagorean triangles.
Okay, so here's where AE equals 1. Can people see that, or is it outside the board, outside the camera? I think it's in. It's in, right?
It's at the top.
It's a little.
It's at the very top. Yeah, I know. Yeah, it's at the very top. Well, this is
It's
you'll
kind
just
of
get the.
halfway.
Yeah. So the main point, all I'm saying is that if AED doesn't have to equal 1, then you could just draw this line so that AE equals 1. I say that it's absurd to say it, but this is oftentimes what people will say when you're working through it. And when you get something like that, when that same kind of thing happens every time, it tells you something about the problem you're confronting. Just like when people say double a square, they go, we'll draw another square. Right? That's what people almost always say. So there's a kind of natural aspect to the way the mind has been trained to think, unfortunately. So the question is not just that AE equals 1, but that both the AE equals 1 and the angle is 90 degrees. So this brought us, so when we first did this, I did this for perhaps for simplicity, to kind of take one direction and exhaust it. But really, since Stewart asked the question, the only real answer for Stewart is why is this a circle, not an ellipse or some other curve, would be to go back to what we said about AED. That it's both always a 90-degree angle, but that the distances are always changing. And so we got, people presented 3 different options. There was a cone for having both circles, circular cross sections, and a changing diameter. Or a cone, a horn, where you have kind of a curved sides, or a sphere. And what we exhausted were the questions that the sphere would be the most appropriate to give us what we were looking for. And that's a tricky area. And the only way to really work it through is to kind of play with it. But what we developed then is if you take our sphere, looks more like a peach or an apple, I guess. I don't like that. Let me redraw it. If you have a sphere where you have a series of, where every possible relationship of AED will always be 90 degrees. If AED is always 90, and yet it can be different lengths, then if this is point A, and these are point B's, then these arcs along our sphere will all be possible E's or epsilons. That the entire sphere, at least in this case, the back quadrant, the back upper quadrant, is all we really need to deal with if you wanted to be specific. But in general terms, if D comes all the way around to the front, and we can go up as well as down, no matter what point E you pick, there'll be some corresponding D that will create an angle that's AED that's 90 degrees. So between a diameter of 2, the diameter of 2, a radius of 1, where D can go from 0 to a length of 2 from A. We go all the way out to the end of the diameter. AD can go from A all the way to B, which is the same thing we have here. It can go from 0, where D is basically at A, and where D is practically at B, which would be 2. We can go from D is basically 0 at A, and it goes around the back end of our equator of our sphere to grow up to the possible length of 2. So from any length from 0 to 2 for AD, we can take any point on our sphere and create some specific triangle that AED is 90 degrees. So again, that's kind of the characteristic of a sphere. We talked about slicing it. You know, it's kind of the funny thing. What if I slice it this way? What if I slice it that way? Well, this sphere is perfectly symmetrical. There's no obtuse angle. There's no way of getting at it, which is anything different than a top-down slice. It's a perfectly symmetrical factor. And it's kind of ironic that notion of symmetry is somewhat, it's a little deceiving. It can become almost counterintuitive. But if that's the case, then this becomes the basis of why we want our Ds to be along a circle. Because it's that circle of Ds along the equator which give us our relationship that AED is always 90. So Stuart, does that answer your question? Or do you want to say anything?
No, that's useful. I had overlooked that 90-degree angle was required, so that's useful.
Okay. Okay, I'm drawing somewhat quickly today because I'm trying to cover all of this. But we're not really rushed. But is anything I've said unclear? And should I redraw anything to make a point clear?
Well, it may be a simple thing that I'm missing, and I know you went through it before, but when you go from the two-dimensional circle where E is to the sphere, I don't quite understand how you define E as being on those circles that intersect. I mean, I understand they're intersecting perpendicularly because in order to maintain the 90 degrees, but how do you define that that those are the E's? Does that make sense?
Right. Yeah. So, I don't know if I can draw it to prove. Well, there might be something I can draw.
Could you
Let
repeat
me,
the question? I couldn't quite hear it.
Yeah, Evelyn, I couldn't. Your box wasn't lighting up. Can you go to the center of your screen and speak up a little bit? It was a little hard to hear you.
Can you hear me now?
No, it's still pretty faint.
Hold on.
Yeah, your box wasn't even lighting up. Just bring your camera down a little bit. For some reason, Zoom has that quality where if it doesn't see your face right, it doesn't increase your volume. It helps, it tries to minimize background talk.
I wasn't hearing you. I think now, can you say
Oh,
something?
there you go. Bravo, there you go, yeah.
What I was asking was, when you go from two dimensions with the triangles in the circle to three dimensions, I got a little bit lost on how. I know that you have to have the idea of circles which are intersecting the circle where the D's are located at 90-degree angles. That's what he was talking about. But why you define that those circles are where E is what I didn't understand.
Yeah, so there's a couple of things that may help with this. One is, I'll try to draw it a little bit better. But let's just take a look at something first. Okay, so here's three very different points C. And this is kind of the old school animation, right? You can fill in the gaps to make it continuous. But you can see that there's a certain kind of interesting trajectory that because D is defined by the point C, and E is defined also by the point C. So AC has a certain angle depending on where point C is. So it's smaller, it grows, and then it grows as C moves counterclockwise along the circle. And so you're getting these kind of unique characteristic triangles, AED. What we're looking at is AED. These 3 points in each case. Now, one thing we know about AED is that it's always a 90-degree angle. So if we're going to think about what defines that relationship in 3 dimensions, where we can say, how do we create all of these possible AEDs for our mind to consider them as a subsuming set, a subsuming hypothesis of all possible AEDs. And that would mean you have, essentially you have a changing degree of circles. Because the 90-degree angle that defines ADE as a triangle, which is always at point E. It's always
you may want to continue, but I just got what you're saying.
Yeah, okay. So these changing circles, so that's why we come up with these possible shapes. So we have a growing circle, which is always subtending that triangle. So you think of, well, what's the idea of a growing circle? So I want to set a 3-dimensional expression, a higher extension of circles, like we did with the sphere and like we did with the torus. But in this case, I need a higher extension of circular action, where the circles are by their nature changing, they're growing in size or diminishing in size. And so you have the 3 hypotheses. You have the cone, you have the horn, or pseudosphere, or whatever, and then you have the sphere. And what we found when we examined this, we took different cuts, that there's only this cut that gives you a circle along the cone. Only that perpendicular cut gives you a circle. And the question is, where would you put point A? Right, we have a hypothesis, because you need something fixed. Right, you think of Kepler's hypothesis of Mars's orbit. Well, he had to first put himself on Mars and get the Earth, to get the Earth's orbit so that the Earth's orbit would be known. But that he needed something to orient everything around. And he didn't want it to be an imaginary point. It was the sun for Kepler. But so A is our sun of sorts. It's our point of perspective. It's our point of measurement. But notice there's no Cartesian grid. I didn't put this in a box. I didn't impose anything on the space by which we're dealing with. We just took some point of perspective, just like you would in a painting. So there's something, these are all lacking, but within the sphere, I can create, I'll use this one. That's a nice sphere. I can create similar kinds of circles, especially if I make my Ds go along the back end of it. So I can draw various points. Oops. I'm going to redraw the sphere and make a nice one. So if I have various points of lines AD, then I know that along the sphere, I have a corresponding arc along the side of the sphere. You can think of it as the side, right? Where I have these arcs, which are all going to be circular arcs. And anywhere on this circular arc, if I take D, the D3 here, anywhere along that arc, that green arc, I could pick some point E. Why? Because at that point E, because it's on a circle with a diameter AD, it's going to be a 90-degree angle. So that 90-degree proportion, that 90-degree relationship, because of the way you can slice a sphere in any way, will always give you a circle. Every point along the sphere is some point along one of these circles, where there's a line AD subtending that as a diameter for that circle. And since every point on the sphere is along one of these circles, every point along the sphere is some possible point E. And that's why we get then a hypothesis of the circle for D. Why it locks it in. The D's can be anywhere along that plane of the torus, but now we have a very clear reason why it should be a circle. Because of the intrinsic ability to use the sphere to bind that relationship to always be 90 degrees. That means we've got our self-similarity of triangles. With AED is always going to be 90. We've now ensured that our self-similarity of triangles, of growth, of our proportions is going to hold. And of course, what do we get once we make D a circle? What does that give us? It gives us something special. It gives us now a very specific point, because if our D's are now going to be a semicircle along the equatorial plane of our torus, where the cream cheese is, to put it in layman's terms. If that's where our D's are now going to be, then it's going to be directly above them. At 90 degrees. We're now going to have restricted. So there was all of the top of the torus. Everything on the top of the torus was some possible C. As is right now, everything along the sphere is right now a possible E. In the case of this process, once we've chose our D's, we also intrinsically chose our C's. There's an intrinsic relationship of D and C. C is directly above C. It's a perpendicular. And that's what gives us that red arc. Or as if you wanted to unfold it, you would say it's the intersection between a cylinder around this circle, this blue circle, intersecting the torus. That's what that red arc gives us. Does anybody have any questions on that? Okay. Well, now we've got our D's, we've got our A, B, C, and D. And that's That's pretty darn close to everything we need. Let me just erase these real quick. And I'm going to draw what I think is at least a helpful visual aid to see the ABCD relationship. Oops, damn. Okay, that might be a little messy, but at least it provides 4 different sets of relationships. So you can kind of see that I've got, along this red arc are all the C's. Along the blue arc are all the D's. And along the green arc are all the B's. And all of them are subtended by some circle going around the torus. And so we've created a very nice set of possible unit circles. We've created an infinite set of unit circles, all displayed in front of us. If we're standing at point A, remember Kepler's hypothesis, right? The harmonies of the universe only are perceivable as if from the sun. It's not the actual motions of the planets. It's the perceived motions of the planets as they move through the arc of vision as if one's standing at the sun. So it's not a bizarre idea to think of yourself standing at A. You can stand on the sun, we can stand at A, and think that you've now got an infinite array of possible unit circles, our old unit circle. But each one is distinct. Each one has a separate B, and for every B, it also has a distinct delta. For every beta, it has a distinct delta and a distinct gamma. So for every single one I'm going to look at, I can look at an infinite set. And for each one, there's going to be a slight difference in the corresponding beta gamma, delta.
Mike?
Yeah,
Yeah, maybe it's good to point out that every one of the A and every one of the D's and B's are on that same plane,
yeah,
right?
yeah, they're all on the same plane. Alpha, delta, beta is all one plane. It's that flat plane along the middle of the torus. Yeah. Okay. So if there's questions, people can pipe up.
I
So
just
then
find
Yeah,
I just find it extremely interesting how this red line is generated, because immediately I thought, well, wait a minute, that's not actually a circle. But then when you understand how it's generated, you realize it doesn't have to be a circle, because that's not where the circles are.
right. Yeah. Exactly. So it's a very anomalous curve. And it's totally physically defined.
Exactly. It's extremely interesting to consider.
Yeah. And that's why I said I'll try to find this video on the Parthenon. It was a nice documentary, but they show that every aspect of the Parthenon, there was not one symmetrical piece. Meaning no one piece was either perfectly symmetrical, and in that way, meaning all of the columns, all of the pieces for the columns. You think of the Parthenon, and you think that it would be kind of like a torus. At least each quadrant would be totally symmetrical. That you could replicate each quadrant. So you build one quadrant, you could build all four from replicating 4 different pieces for each one. Minimally, there'd be that symmetry, let alone the columns maybe might even have greater redundancy. There wasn't one piece that they found that was replicable for any other. So this idea of defining something of physical geometry is a natural way of thinking, but it's totally not mathematical. It's not a mathematically describable curve the way we would think of things. Okay, so let's look at the, my circles are I'm getting too much time at the whiteboard. Okay, there we go. Yeah, I'm getting more eggish. My circles are getting more eggish as we go. Okay, so we go back to our sphere, which was always kind of the funny thing. If you didn't have the sphere in mind, then I often think that this is where, it's kind of like that fifth voice maybe in the fugue. Okay, so we know we have D's, and then everything on top is our E's in every direction. No. And so on. Everything along the surface of the sphere are E's, are epsilons. And deltas are along the equator. And we know that for every possible E, there's always a D, which will make the AED, the alpha epsilon delta, make that angle 90 degrees. Because it's an intrinsic property of the sphere. So the natural tendency would be to say, well, let's just pick a spot where the alpha epsilons are equal to 1. And that's where you get this process. And so when we do that, when we let alpha epsilon equal 1, and it becomes that arc along the sphere, so that we take that length of 1, which is our radius, we take it over to the edge of our sphere along the equator. Right, so right now it's going through the sphere on the diameter. We take it over to the surface of our sphere at the equator, so it meets a point D. And then we just maintain that length as we trace an arc along the surface of the sphere. Why the surface of the sphere? Because everywhere on that surface, that angle, alpha epsilon delta, will always be 90. So we create a set of points, which is this green arc, which are both AE equal to 1, and that angle, alpha epsilon delta, is equal to 90 degrees. That's what that green arc gives us. So Archytas realizes that at that point, everything comes together. It fits perfectly. All we have to do now is build our cone, this cone, with point A at the same location, and it will intersect some point C. So I'm just going to draw that as nicely as I can, and then we'll see if there's any questions.
Are you taking questions?
Sure, go ahead.
Okay. Well, there've been I know in different sources, I don't know if it comes from whatever the original source or original sources, so to speak, for Archytas's solution. I don't think they're fragments. I think they're, secondhand, right? So, but, in all the diagrams I've seen that are attached with that kind of source material, it just shows the cone, the cylinder, and the torus, or at least like a triangle that's, forms the cone plus, the other two. But, they don't really have the sphere.
No, no, they don't. You don't, because you don't need it. That's the point. You don't need it in the to define point C. That's why I say it might be the fifth voice of the fugue. So there's a certain kind of concept, say, of the fugue. There's a certain interplay of voices that Bach has that's kind of shaping how he might unfold each of the individual voices. Say it's a three-voice fugue in this case. So it's the higher voice, the fifth, so-called fifth voice. So that there's an underlying question, but it's not in the composition, but it's in the mind, and it's certainly governing how this unfolds. It's also a characteristic of how we go from a unit circle into an extended space, an extended dimension, or higher extension, you might say. It's going, obviously, from going from the circle, we go into the sphere. So it's an underlying question. But when you look at the points, let me draw. when you define the point C, you're going to be moving. You're starting at this point along the cone or along our sphere. We're going to move up along the sphere and down along that arc of the sphere from the back of the equator towards the front of the sphere. And as we move along that, if we do it from the full extension of our cone, then as we move up, there's going to be some line which is going to intersect. There's only going to be one point where the extension of that cone, as we hear it, this is just the top of the cone. There'd be a bottom of it also, just more difficult to draw. There's only going to be one spot where that cone intersects that red line. Now, that might seem obvious to people. In previous discussions, it's hard for people to imagine. I've often said, just put yourself at point A, imagine the red arc, and imagine creating the cone with your arm. And you'll have some, I think, some ability, some visual relationship to see how there only one point can be intersected. And because there's only one point, we've effectively defined that one point C where all of our relationships exist, A, B, C, D, and E, along that green arc, are all created, all 90 degrees, and where AE equals 1. And so you don't need the three intersections. You only need the three surfaces, the cylinder along the blue circle, the torus along the red circle, and then the cone along the green arc. The intersection of those three surfaces, just like any three rotations, will generate some particular point in space to define our particular point C. And it's kind of beautiful. It's kind of beautiful. But like I said, I think there's 2 points to this, and I'll see if there's any thoughts or questions. One is just kind of understanding it, seeing how it works, knowing that you can replicate each surface to generate it, and that you know that when you generate them, you're getting these relationships. And then the deeper question comes in is, what quality of thinking? What does this suggest then about Architas's method of thinking? Which is ultimately the pursuit. But it takes the amount of work to know just the natural truthfulness of the proof, that it actually does do what we say it does, which you want to first resolve. And then the question comes in of by what means, and not so much by what means, but by what quality of thinking. And I'll just point out, there's, like I said before, I didn't put this into an X, Y, Z coordinate. They do today. If you look at like a modern math course, if they dealt with this, they would just look at the formula. There are parametrics for a cone, a torus, and a cylinder. They'll put those in and find the point by which they all intersect. And it'll be put into a three-dimensional parameters. This is why Leibniz's intervention on the catenary was so important, because it brought back this pre-Euclidean approach. Though this isn't physical space, why it's so profound is that Architas is actually able to become at least tangential with the way of thinking about physical space. Where when you're dealing with just 2 dimensions in a square, it's pedagogically interesting, but it's fairly removed from actual thinking about the physical process. This is as if it's tangential. It's not quite there. You're having to assume flatness in the very small. to get that tangential relationship. But yet it approximates it. What Leibniz does with the catenary is he does not introduce a coordinate system. You would say he does, and there are aspects of it which help to advance the language. But ultimately, Leibniz's view is that we're going to measure the catenary from on the catenary.
Yeah.
We're going to let the catenary define the space that has determined the catenary. The catenary is an expression of the physical space itself. When you look at what Euler and Lagrange do, when you look at what someone like Richard Feynman does in terms of advanced, modern physics, and they're kind of Max Planck references this principle of least action. But what Euler and Lagrange do is they take Leibniz's catenary and they put it into this predefined space and define the catenary and define least action from a coordinate system. And it's something Phil was raising when we talked earlier today, which is just a profound quality. We've done everything from from physical relationships, even though they're simply geometrical. They've taken the place for a physical conception. And we've allowed those physical relationships to define our resolution. We don't have to put it into a defined space. We let the interplay, the compositional interplay of the three surfaces, which are generated from a set of relationships, define the physical space we're confronting. And I think that's an aspect of this pre-Euclidean thought, which is, as we know, very intrinsic to what Lynn was always developing. So I'm going to leave my comments there and then see if people have thoughts or questions.
Question. I think that if you would simply finish your class, you did excellent class, by physically doubling the cube, like take a cube, see, and then with all of your drawings, double it, fill up one with water or whatever liquid, and then pour it into the other one that you claim is your answer, representing twice the volume, and see if your first cube empties twice into your second cube. Okay, that's the question. And the reason why is that it does work and there is a way, and you should finalize by making one physically. All of your instructions are useful, good, getting people involved and looking at the dimensions. But the final proof, to quote LaRouche, believe nothing that for which you cannot give yourself a constructive proof. Please, why don't you build the first cube, pour it into the second cube, and see it go in twice. And if you need help, I will show you how to get the answer, because your diagram, A to epsilon, if you count it as unit 1, will not give you your answer. This, which I'm holding here, and I can show to you, if the circle, radius 1, is your cube 1, then you take what's called the golden mean of your diameter and swing that up, and that will give you your cube 2. Yes, the golden mean. As in Plato's Platonic solids, when you mesh all 5 solids intermesh into each other, the 4th solid to the 5th is only done by the golden mean. That idea, when you apply it to Alcides, who is a friend of Plato, who bailed Plato out when Plato was imprisoned in Syracuse, Alcides wrote that letter saying, release Plato.
Yeah. I mean, look.
Now, the question is, would you please show to the people how to double the cube?
Okay.
Can you do it? Have you ever done it? And can you do it now to finish your class? Or will you only have the diagrams?
You need to calm down a little bit. So, look, I think it's a good challenge for people, what you're making, which is that they can certainly do that. But there's a higher principle than simply just doubling a cube, though it's a question of investigation of the physical universe. And to that extent, what you're referencing is important. But I think that you made your point, and I'd like to see if anybody else has thoughts or questions. Everybody's happy, everyone's content, everybody wants to go build their own double-sized cube.
Well, I have a question, I guess.
Sure.
When you say that the sphere is not essential, here's what I'm thinking what you mean, that you take we got A to B is the diameter, and that's 2. So 1 obviously is the center, and you move that over to the circle. I'm just thinking that you do need the sphere, because you're moving
Yeah.
one.
Yeah, I mean, I'm not saying the sphere is not essential. It's like saying that the higher voice, the interplay of the relationships of the voices is not essential in composing a fugue. Right? If a computer composes a fugue, does it have the 5th voice? If a computer composes a 4-part fugue, if you program it to compose fugues, does it compose around a 5th voice? Now, that's an interesting question. But in general, you're saying that you'd have to program it to look at the 5th voice. And then you'd have to figure out if you can even program a computer to look at the 5th voice. Or is that something unique to the human mind? The point I'm making is that the sphere is not what defines that particular point. That's what Bill was raising. But the sphere, that there's the intersection to define that point C, the big question of what point C does it? Because what Eli's referencing, and I mean, I have to take this up in a certain sense, you can construct, if you do your design effectively, you can construct a cube of double the volume simply from the unit circle. Simply from a method of exhaustion, you could construct a cube within clear limitations that would ultimately be double. You could find that particular point C, and from that construct a point D that would solve the problem for an engineering construction. But Archytas is not getting at the question that the Greeks actually need to build a higher altar. What Archytas and the collaboration with Plato is, there's a loss of a quality of thinking about the physical universe. So in that sense, the sphere is part of the composition, right? It's intrinsically part of the composition. It's intrinsically part of where he gets the cone. If you don't have the sphere, you'll never really resolve where he got the cone from. You can kind of do some hand waving that might be sufficient, but to really understand where the cone develops, it develops out of the sphere. It's an intrinsic part of it, but it doesn't define that point in space.
Well, when looking back, I missed the beginning of the first class, so I had to go back and watch it. And when I saw, the A to E, all of that, I was completely dumbfounded, and I thought what you just said, which is, what more do I need? This is it. I can do it, right?
Yeah.
And now that you've put me through this torture to see how to do it, I believe, the difference between the fantasy of just doing it from the triangle within the circle and what Archytas has done is that this is 3-dimensional. It's not on a flat surface, that you're actually building a physical existence that measures up to everything that you're trying to do. You know, like from the perspective of A, you're looking out into a spectrum of activity that intersects at the particular point that you're looking for. So it's like very exciting.
Yeah, yeah, no, it's very exciting. And the question is that there's a difference. There's a kind of knowability just in the unit circle, right? There's a knowability of proportions of triangles. There's a knowability of proportions of length. And if you have enough precise instruments, pencils or pens or carving material and straight edges to a certain tolerance, you could ultimately solve the problem for all practical purposes, emphasis on practical purposes, of doubling the size of the volume of the cube or the altar or whatever challenge you wanted. That would be sufficient. An engineer would need nothing more. An engineer doesn't need this. It's completely irrelevant to an engineer. And yet, what is Kepler asking? Kepler's asking, he first has to figure out what the actual planetary orbits appear to us as. Can we forecast precisely what they are? And he does all kinds of corrections in that regard. But then he has to say, what's the truth of what's the actual nature of their actual orbits? What's the truth of their orbits? And then he asks the question, what's the truth of not just their orbits, but their motions? Why do they move the way they do? And so he's asking the questions of knowability of the universe itself, that the domain of principle is accessible. So the difference between the unit circle and Archidas' demonstration is the difference between practical questions of daily life and the questions of the domain of principle. And there's clearly an aesthetic, as you're getting at, Mike, an aesthetic question, the same point Einstein makes, of what allures us to that higher domain of principle, what gives us access to it, and what allows us to find it to be knowable and communicable is some aesthetic characteristic. One that clearly has a kind of polyphonic or compositional quality. And that's what and only through that means, only through that pathway, do we get precise understanding, not approximately where C is to a tolerable degree, to simply double the altar, but that we can say we know we have accessed the domain, a higher domain by which such things can be known with great precision. And so in some ways, it's a demonstration of a going from right opinion or right belief to true knowledge, which can be infinitesimally different. And yet the impact upon the human identity and upon human society is profound. And that's what Archidas gives us access to. So I hope maybe that expands the point you were making, but it's
Yeah.
Michael,
yeah.
can you just go over briefly again why that point C that we defined satisfies all of the requirements in terms of those ratios that you have to have for try to arrive at a doubling with a volume?
Sure. Okay. That was Dan, right?
Yeah.
Okay. So Dan, you grasp the idea that, because I've drawn at least the basic relationships here of A, B, C, and D, where I have the intersection of the torus and the cylinder along that red line. Does that make sense that this red line is the intersection of the torus and the cylinder?
Yeah.
Okay, I don't want to assume anything. Okay, so this red line is the intersection of the torus and the cylinder. And when we look at that red line, you have A, you have a B along that back green line, you have a C, and you have a D. And they all have the relationships that they would have in our unit circle. So then the question is, when we introduce the cone is based on what construction, what principle of construction? One is that A alpha epsilon delta with D along the equator is always 90 degrees. So any point E along the sphere, no matter what, there will be some delta along the equator that will make the angle alpha epsilon delta always 90. So now we've gotten that. We've got 90 degrees always for AED. When we draw the green arc, we've said everywhere along the sphere where alpha epsilon equals 1. So when we bring that same green arc along the sphere over here and we extend it out, right? So we make the cone longer. Our epsilons are still along this green arc. This is where our epsilons still exist. We just extended the cone so that we can intersect the red line or the red arc. So when we do that, when we extend the cone out along this line I've drawn, that's where we intersect the red arc. At that point, this is a point C. It's got a corresponding point D. It's got a corresponding point B. Let's just draw it. Here's our B. Here's our D at 90-degree angle. Here's our C at a 90-degree angle. And then this point D to this point here, our epsilon, is also going to be 90 degrees. Because we know it's true. We know along that green arc, from that point D to that green arc to alpha is 90 degrees. And we know that along that green arc, alpha epsilon is always 1. So every A, B, C, and D are all consistent. We've got those relationships here. Once we find the intersection of the cone, then that point D below that point C has a relationship to that green arc, which is 90 degrees. Is that clarified, or is there still something confusing?
Michael?
Yeah.
So the AED is on a different plane essentially than the ACB, right? And ACD? Am I right about that, or is that wrong?
Say it again. Say it again.
Is the AED on a different plane than the ACB, or is it just the
No,
way?
it's just my drawing.
Okay, I just was
Proportions of the drawing got a little funny, so that angle looks a little warped. But
okay.
no, it's the same. My black marker also went kind of dry on me.
Okay.
Give me a second. I'll get another black marker. Dan, what do you think?
Well, last week you actually restated the ratios
Yeah.
that you started out with, that you have to have for the doubling of a volume, or well, of cubes, where you showed the two means.
Right. Okay, yeah, I can do that. So if we have oops, sorry, that's wrong. Okay, so there's our 4 proportions: alpha epsilon, alpha delta, alpha gamma, alpha beta. And they're all along the same plane. If you could take a plane and go right through that line ADB, and they would all fit on one circle. Just like this, Belinda. They would all fit on one circle. And with AB we know is 2. It's the distance of our diameter. The question was, can we let AE equal 1 and be 90 degrees? If we've solved that problem, if we've intrinsically resolved it, by the way we built the cone in such a way that AED is both AE equal to 1 and AED equal to 90 degrees. We built the cone that way. So when the cone intersects an arc along the red, a point along the red arc, it intrinsically solves the problem. And you get AD becomes has a magnitude of the cube root of 2.
And we,
This is a little sloppy. I should redraw that, but go ahead.
I was just going to say, if you look at AB and you're moving it now in the torus, and you're going through a whole series of ACBs, right? Then until you come to the right angle, which has exactly what you want. The AE, you're now intersecting 1 for AE, and you're at the triangle that we started with, saying that, we have to find the right position. So the question, I guess the question I'm asking is, can you determine what angle you're looking for? What's the angle that, I guess not. I don't know.
Oh, you mean what's this angle that gives us that particular C?
Yeah.
Yeah, no, I mean it's not I'm sure you can mathematically work it through. I haven't.
Okay.
Yeah, I can't tell you what specific angle that is, but I'm sure it's just I'm sure it's probably knowable in some form. I mean it seems like a complicated challenge or a good challenge, but I couldn't tell you what angle it's at.
Well, the interesting thing though is what you said, putting yourself on the sun at A, and looking out as the proportions shift into exactly what you want, and then bingo, we're here. This is it. Yeah.
Right? Right? Dan, does this answer your question, resolve your question of how these proportions are the
Yeah.
proportions that we were building?
That's what I was looking for.
Okay.
I still can't figure out how you would construct the cube.
You can't figure out how to construct. Oh, you should ask Eli about that. No, I think that well, what do you need to build a cube, Dan?
You just need an edge.
Okay. So you'd have to construct this. This is what Eli has been doing. You would construct this in some way. Right, which is possible. But do you see how we have an edge? Do you see that by this method we have done a physical demonstration of how you would construct that edge?
Yeah, I'm having trouble seeing it.
What edge do you think doubles the cube?
The edge would be AD.
Yeah, is that Dan though?
No, it's
No,
Art.
that's Art.
Oh, yeah, I was asking Dan.
AD. Okay.
Yeah, do you see how the purport, because that's why I did the introduction, but it's this,
Okay,
This
yeah,
is the-
AD. Now I see it.
this is the cube, this is the edge of a cube of 8,
Mm-hmm.
right? This is the cube of an edge of 4, this is the edge of a cube of 2, and this is the edge of a cube of 1.
Right, okay,
Right,
now I
so
see.
you double from 1, 2, 4, and 8. And you bring it down to the edges. So in the way we've set this up, AD, the length AD, would be our cube root of 2.
Okay, now I get it.
This
I
may
just
sound,
I think
this may sound funny.
Dan
Oh, I'm
has
sorry.
there
Go
is
ahead.
that you know, the cube root of 2, that's the name, just the name for what it is we want. But if you actually build the construction, you can measure it, and you can actually build a cube with that size. Because the cube root of 2, nobody knows what the hell the cube root of 2 is. That's what we're trying to find out to begin with. But here you have, it's just a name. But
Yeah.
if you actually construct this, then you can measure it.
Right.
You can actually physically build whatever it is that you're trying to build.
Right. Right. Yeah. But again, I mean, it's not a question of an engineering practice, because you could do that just to make the point, even if it's very polemical or provocative, is that you could ultimately do that with a measurement of tolerance of measurement with just the unit circle.
I was going to make a comment.
When you physically construct this, you're going to deal with similar restraints of your ability to build it, where you're still going to have to do it within a certain tolerance. And so it's a different question that we're accessing than simply doubling the volume of a cube. So what you're looking for is two things. One is to logically understand that we defined the problem a certain way and found a way to resolve the problem with great precision. So we solved the question of what point C. And if you did the method of exhaustion, that'll be clear. If you didn't do the method of exhaustion, then when I keep referencing that, it'll be like a foggy mess in your fog. It won't have the specific reference. But if you have that point C in your mind, then you'll see how we've logically solved this. But then logically solving it isn't where the substance lies. It just means that you've opened up the door to asking, what is Archytas demonstrating about the way we think about knowing a domain of principle? And I'm not going to let that point go. As much as I want people to see how it does solve the doubling of the cube problem, you don't want to get caught on a cube. But you still need to know how it logically works. Okay, any other thoughts or questions though?
Well, Mike, I was going to make a simple comment, which is like what you're saying. If you are somebody who has designed a machine tool, the machine, when you use the machine tool, you have a certain amount of tolerances you have to go to, like 10,000ths of an inch, which is the approximation of what your idea is. Your idea is what came first. The concept of designing the machine tool is sort of the ideal, like the, and if you have this, so Archytas gave you the idea of how to design the machine tool. He didn't build it, but he designed the concept, right?
Yeah.
I have a historical question.
Yeah.
If there's time. Leonardo was, I would say, in love with this question. And from at least what I've seen, and of course, most of his work is hidden in the, in the Queen's chambers. So we haven't seen everything of his yet, but we will. But he really worked through this in all kinds of very interesting ways. However, I have not seen this kind of construction in his work. Also, Dürer also did quite a bit of work. I wouldn't say that he, at least from what I've seen, that he was as, as broad as Leonardo was. So what I'm wondering is, historically, when was this lost and when was it regained? I think that you've pointed to, and maybe I've seen it written, just stated, that Kepler had a greater idea of this construction. But I'm wondering when it was lost, because obviously if this this was put forward during Leonardo's time, he would have definitely gone through a class like you have for the rest of humanity and maybe even made another level. And then the other thing that I just have to say, which is more linear, is that a lot of what you've done reminds me of the stereographic projections that are used in the construction of an astrolabe. So
Right.
what do you have any thoughts about this, when this was lost and how it was regained?
Well, I have to say that the method is lost with the introduction of Euclid and the Ptolemaic kind of control. And that really is a turning point. You know, it's subsequently around the time, you know, we lose Archimedes, the rise of the Roman Empire. So the loss of it is certainly there. But it's regained, I don't know. I mean, someone like David Shaven or maybe Bill Roberts, who's referenced some of those questions, may know when it was truly revived. I mean, we know that other people look at the problem. We have Menaechmus, we have Eratosthenes. They looked at the same problem. So the problem lingered for quite some time. And as a verbal representation, that Archytas, I mean, I've seen these verbal representations. Archytas solved the problem with the intersection of a cylinder, a cone, and the torus. So that might have lingered, but when it was actually revived and it became part of a language, a discourse of, say, mathematics, or at least within the field of mathematics or quality of thought, I don't know. I don't know when it's first revived, re-encountered, or developed. And by who? I don't know. That's a good question. And maybe somebody knows, and it's a question maybe to put out there to people. And in terms of the astrolabe, that's provocative, and I think there's probably a lot of references, because this is just a higher way of thinking about solving physical problems. But I couldn't say more, but I find it provocative, what you said.
Mike, I have a short comment, just to kind of a thanks for your class, because it was really great. And my thought is, as you've pointed to throughout the class, none of this is actually the substance of your class. The substance of your class was the playfulness with which you approached it, approached the question, and which you shared with us. And that reflects in the way that you actually make the proof, in that none of the objects, so to speak, are actually real when you go through it like this. The cylinder is not real, the cone is not real, the torus is not real. They are just generatives of a principle of mind that is striving towards this question, solving this question. And they don't really exist in and of themselves, but only in this generative playfulness. So that was what I got out of your class, and I'm very thankful for that.
Oh, that's good. That's very thoughtful. I mean, it certainly is the case that the surfaces really are the shadows, or the sense impressions of or you might say the residue of the actual proof. I would say that's absolutely accurate, and I think that is certainly how I probably have thought about this. And certainly obviously it comes more alive as I teach it more, but it's certainly the case that the surfaces themselves are just residues, the footprints left in the sand by the principle of the interaction of the relationships. Because that's ultimately what we're defining. I mean, Einstein's question is a question of relationships. There is nothing that's a static just existence. You have, ultimately the proof hinges upon relationships and the way those relationships change as they move through a process of motion. And we played with that interaction.
Would you say?
Yeah, go ahead.
could you say that this is a reflection in the visible domain of the intersection between these principles of rotation and extension?
Yeah, and that they're just that notion of rotation and extension are now bounded by the particular relationships we identify. So we said there's a set of relationships here that are intrinsic to the idea. Now we have to find a way of finding the appropriate way of defining those relationships. And that comes from an interplay of an interplay between the various sets. In the easiest language is the language of a musical process of the interplay of these various voices. If the voices have a certain relationship, you think through the rehearsal of a choral piece. You pull out, you listen to the bass and alto, tenor and alto. You define there's a set of relationships, but then you have to kind of compose them as a singular one. And what we've done is we've extended these relationships, the ABC relationship, to put it in, say, specific representation. The ABC relationship was extended as the basis for creating that, you could even say the toroidal action, right, which gives us the residue of a torus, but ultimately we gave ourselves a sense of motion, through a sense of motion, a new degree of freedom between A, B, and C. And then in that process, we had to define, based on the relationships of C and D and A, B, and D, we had to create a different set of relationships and how those things might interplay with each other. And that kind of tempering, think of Kepler's fifth book and the harmonies, and you see a similar characteristic of interplay of planetary relationships. So that helps us to achieve a singular idea of a one governing principle of the solar system. And you could say the same thing with Einstein's question of the relationship between the Earth, the Sun, and Mercury based on the visible questions of light and gravitation. So there's spatial relations that are moving, and yet there are also then these characteristic relationships of both the principle of gravitation and light, which give us that subtle difference in Mercury's orbit or Mercury's appearance. And so it's that quality of thought which really is at play, and I think that's probably a good place to end unless there's anything else pressing.
Well, just two things quickly.
I would like to make a comment.
Okay, go ahead.
Simple. It is not the school of absorption that will not double the cube. The diagram of Archytas does double the cube. It is not absorption. 2, if you double the cube, take the diameter, A, B, diameter circle, divide it into its golden mean. The golden mean will double the cube. That is not absorption. It is very specific. And ask yourself the question, if it's triply rotational action, which LaRouche referred to many times, and if that drawing of Archytas actually doubles the cube, then ask yourself a question. Are you looking at a multiple direction of rotation of something like solid matter, like rocks, stones, or the 5 platonic solids? Or are you looking at a drawing of a skeleton of something that was living, like seashells? If that were true, and what I first said, to double the cube, take your diameter, divide it by its golden mean. The golden mean will double the cube of its radius. That's right. That's how I built my construction. Okay. 2, as a principle, that's not school of absorption. That's very principle. You see it in the 5 platonic solids. But you see it in seashells, because why do seashells know how to double the cube? Second thing. So If it is that way, there's a principle behind that Archytas drawing, friend of Plato. There is a principle, and that's a real drawing that doubles a cube. That's not a daydream, it's not fake. That's my comment. If anybody wants to talk to me, you could email me or call me up and I'll show you how to do it. Just listen to what I just said and do it. Take the diameter, AB, get the golden mean. The large part of that golden section is going to double the cube. If your radius is unit 1, make a box. The golden mean, it'll be unit 2, and there it is. Okay, so that's my answer.
Okay.
I hope you have a lot of fun. Bye.
Thank
Bye.
you, Len. Thank you.
Two things. One is I really appreciate also this class. I mean, for some reason, I always had in my head sort of that the solids came first, the torus and the cylinder and the cone, and it didn't make any sense to try to figure out how to fit them together without the conception. So that was very helpful. And secondly, I want to make a joyful announcement, which is that President Trump commuted the sentence for Roger Stone.
All right. Here, here. One down, one to go.
That's right.
Lynn is next.
Yes.
That's right. Yeah, we're tangential. We've now got to get to the real higher domain with Lynn. Well, good for Roger and good for mankind. We've got a president who's fighting. That's good.
Yeah.
Okay, and I think there's probably nothing else pressing. I leave everyone to Eli's challenge to double your cube. But most importantly, try to, work this through with someone. Your friend, your colleague, a contact. But just try to work them through and communicate it, because it can be a basis of discussion. And what you'll run into is where you fall into traps where you're not clear on something. That's where it gets fun. Okay.
Thank you.
Thanks, guys. Take
Thank
care.
you.
Thanks a lot, Mike.
Thank you.